Good evening, Herefordshire. A pleasure to be back once again to give you the rather cryptically titled 277. And yes, this is about the 200-inch Palomar telescope, ultimately called the Hale telescope, as it is now 77 years old and still going strong. My love affair with this particular telescope didn't start in 1951. That's when this image was taken. But I remember seeing this image in a book in a library at school. I think it was the Atlas of the Universe. I saw this image. I'm not sure exactly how old I was at the time, but I thought, wow, the universe is full of really interesting stuff. Why does the universe decide to make lots of clouds that look like chess pieces? What's it actually made of? How did it come to be? How is it changing? This, more than anything else, sparked my interest in astronomy many years ago, 50-something years ago. I can't quite place the year. But I'm talking about this telescope and the person who put it together, George Ellery Hale. He was a billionaire whisperer. He managed to get funding to build the world's largest telescope. Not just once, not twice, not 3 times, but 4 times he built the world's largest telescope. He built the 40-inch Yerkes telescope, and then he went on to build the 60-inch at Mount Wilson, then the Hooker 100-inch, and what I'm talking about this evening is the 200-inch telescope. So I'll be talking about how that came to be, briefly, because George Ellery Hale's life is interesting and could be another 2 or 3 hour talk in its own right. But I'm going to be talking about the 200-inch telescope, how they decided where to put it once they got the money for it, how they made the mirror, and how they made the telescope itself. I'll be saying a little bit about what it's doing now, 77 years on, and then I will give some acknowledgements right at the end. So, George Ellery Hale, you can see the dates of his life there. He had a remarkable life. He was a good astronomer in his own right, in the sense that he pushed the science forward. He was actually interested in the spectrum of the sun and ultimately the spectrum of the stars to try and understand composition and other physical processes. But he's remembered more than the inventor of the spectrohelioscope. He's remembered for being the person building these large telescopes in the opening decades of the last century. So the largest telescopes in the world, the 40-inch Yerkes, this is the last one with a very large lens, so we're talking 40-inch lens, before moving over to mirrors, which are much easier to make when you're talking about diameters that are substantially bigger than 1 meter. So the Yerkes Observatory, that was operational as of 1900. He then obtained some funding to build the 60-inch reflecting telescope in Mount Wilson. This is when he was the director of this particular observatory. And then he went on, and in 1918 he commissioned the 100-inch Hooker telescope, so named after the person who basically provided the money. So there was this series, and you notice that the aperture goes from 40, roughly half as much again, to 60, roughly half as much again to 100. And so if you think, what's the next logical step after building these 3 telescopes, you would think the next logical step would be to build the 150-inch. Remember, if you increase the diameter by 50%, you're effectively doubling, or a little more than doubling, the area. But at the time the Hooker was being built, Hale was already thinking beyond that. He didn't simply want to go with the status quo, which would be 150 inches the next logical step. Even as soon as the Hooker telescope was operational, possibly even the next night, he was saying, we need bigger telescopes. Basically, we need more light. He realized, as much as any other astronomer, that when you're dealing with either very remote galaxies, or even if you're dealing with, I want to get the spectrum of this not particularly bright star, aperture is everything. It's not always about detail, it's sometimes simply about flux, capturing as much light as possible. And he realized he wanted more and more light. So it took him a while, but in 1928 he approached the Rockefeller Foundation. In previous guises, he had gone to people like Carnegie, anybody with really deep pockets. The Rockefeller Foundation had plenty of money, but he still had to convince them, please give me enough money to start building the world's largest telescope, which is going to be twice the diameter, 4 times the area of the existing world's largest telescope. Somehow he managed to convince them to put up the entire amount of money, not just to build the telescope, not just to build the telescope and the dome in which it was going to sit, the entire observatory infrastructure at a cost of some $6 million. In 1920s money, that is an awful lot of money, especially during the middle of the Depression. That's something like, I think you can probably multiply by about 100 or so for today's money. So that's something like $500 million was put on the table. Yeah, great. Sounds like a good idea. Go for it. It's a bit more difficult to get funding these days, especially at that sort of level. So he obtained the funding, and then the question is, right, if Rockefeller are happy to put all the money up, where are we going to put the world's largest telescope? Well, Hale had a somewhat parochial view in the sense that he believed all of the world's best astronomers were in Los Angeles. Now, you can argue whether or not that's the case. There were certainly a concentration of American astronomers in California, but he believed that he didn't want to oversee a project where the telescope was built on the other side of the world, whereas he was based in Los Angeles. So he basically wanted somewhere relatively close to home base. So there's Los Angeles and the island of Catalina just off the coast there. And Mount Wilson sits just to the north of Los Angeles. And you can see the size of the city is huge compared to Mount Wilson. And not surprisingly, Mount Wilson, although it was quite good when it was started, is being encroached by all of the light pollution of Los Angeles. Not only that, but more recent light pollution from San Fernando and San Bernardino. Effectively, they are now wrapping their way around Mount Wilson and effectively destroying the clear skies. So he decided it has to be somewhere else. Mount Wilson would be great, nice and close to home, close to the Caltech, close to the Pasadena workshops, etc. But we need to think further afield. So he sent scouting parties out to the mountains in the southern part of California and tried to find mountain tops which had really excellent seeing. He found a few possibilities, and he consulted with his colleague in Caltech, the head of the Department of Geology, and said, what do you think about these possibilities? At which point, the head of geology, who was Richter, yes, he of the Richter scale, said, I wouldn't choose that one if I were you. Why not? It's on the San Andreas Fault. Okay, yeah, right, good point, well made, we won't go with that. But what about this one over here? What about this Palomar Mountain? Richter said, great idea. Palomar Mountain is a slab of granite, 30 miles long, 10 miles wide, 25 miles deep. It is trillions upon trillions of tons of granite. If California has an earthquake, that is not going anywhere. If you bolt your telescope mount to that, you're going to be in business. So it was decided to go with Mount Palomar. There is the slight problem of San Diego to the south. Perhaps you can see from the scale, there's a 20-mile scale bar there. San Diego is sort of 100 miles away or a little less. And yes, it will spoil the southern skies, but San Diego at the time wasn't a very big city. It, of course, has grown in the intervening century or so, but at the time, that was considered not to be a problem. So what did Palomar look like? Well, that's what it looks like now, or at least that was a few years ago. A beautiful site, especially if you visit it at the right time of year. I visited in the spring in 1982. That's me there as a student. Yeah, I think I'm wearing the same shirt. That's not altogether surprising. So, yeah, that's 1982. And at the time I said, what a fantastic thing. The world's biggest telescope in the world's biggest dome. When I buy a house, I'm going to have a garden big enough for a dome like that. Okay, it didn't work out that way. But remember the altitude. It's on top of a mountain. It's at 1,700 meters, or about 6,000 feet or so. So it does get very cold in winter. And you have to pay people to shovel snow off the dome. Otherwise, the mass of the dome simply increases if you have a heavy snowfall. That's, roughly speaking, what it looks like. This is what it looked like at the time. There was nothing on the top of Mount Palomar. It was basically just a tourist attraction for people to visit. 6,000 feet or thereabouts high, and the only way of getting stuff up there, I must remember the laser doesn't work, the only way of getting stuff up there is to take it up this rather windy road, not tarmacked, just basically a dirt track. So everything, not just the mirror, not just the telescope, not just the bits of the dome, the entire observatory infrastructure had to be taken up that windy road until they could eventually improve the infrastructure of the mountain. Okay, so you've got the money and you've decided where to put it. Problem number 3 is, how are you going to mount this telescope? It's going to be the world's biggest by a lot. It's not going to be just a little bit bigger. It's going to be 4 times the area and possibly twice as long. It's going to be 10 times the mass or something like that. So how are you going to mount it? Well, we as amateurs know that there are a few possibilities for how you can mount a telescope. If you're going to have an equatorial telescope, a German mount requires a counterweight. If you don't want to have a telescope and a big counterweight, then you could go with a fork mounting, and the English or yoke mounting is effectively 2 forks back to back, which has the advantage that you support it at the south and the north end of the mount, and you distribute the load. You can take much heavier loads in a yoke mount. And if we see, rather interestingly, the last 3 telescopes that were in turn the largest telescopes in the world, the Yerkes is on a German mount, the 60-inch at Mount Wilson is on a fork mount. It's only a very small fork, so it might not look like a fork mount, but it is. And the Hooker telescope was on an English or yoke mount. So Hale had already, in a sense, used each of the 3 possibilities for how to make the world's largest telescope. So where do you go from there? If your telescope is going to be a lot more massive, what are you going to do? Well, Hale decided that, partly because of his age, this is probably the last telescope he will ever build, certainly the last one that he can claim to be the world's largest telescope. He didn't want it to suffer from the same limitations as the Hooker telescope, finished in 1918. And the Hooker telescope has at least 2 limitations that he was aware of that he wanted to try and circumvent. One was the fact that it's on a yoke mount supported at the south and north end, and that meant, if you look at the length of the telescope itself, the telescope could not point at the North Pole because it simply clouted the actual yoke mount itself. So there was a no-go zone. It was about 30 degrees from the pole. So there was a disk of sky, 60 degrees in diameter, which could never be viewed by the 100-inch Hooker. And it doesn't matter if a supernova goes off there or something interesting happens, the telescope would never be able to track to that bit of sky. Not only did he want to get around that problem, he wanted to get around the problem of the fact that the mirror, the 100-inch mirror, was made of plate glass. And plate glass has the problem of expanding and contracting as the temperature changes. And if you're trying to make a nice shape that perfectly focuses light, the last thing you need is for the night temperature to be a little different from what you were hoping it was going to be, and then you have to wait until the mirror cools down or warms up to the same temperature as the nighttime air. And in some cases, that could take many hours. In some cases, it might take 6 hours for the mirror to adjust the nighttime temperature. So it might be that half the night was wasted just waiting for the mirror to cool down or warm up such that the shape was right. If you try and make any observations whilst the mirror is still expanding or contracting because of the change in temperature, it won't be the right shape, and therefore you won't get nice images. You won't get nice sharp stars. Let's deal with the first one first. How do you get around this problem of not being able to point at the pole, but still the idea of a yoke mount where you're supporting the telescope on both sides, and ideally supporting the yoke at the north and the south end of the mount? That gives you the greatest stability, but how do you get around to the problem of not being able to point at the North Pole? It was decided to adopt the iconic horseshoe mount. And you can see the yoke mounting, cylinders either side of the telescope, a simple mounting at the south, but a large horseshoe on the north side. And that meant, if you so desire, the telescope could be swung until it nestles inside the horseshoe and allows you to point at the North Pole. So none of the sky is out of bounds. There are some bits of the sky where you have to wait for the sky to rotate, for the star or the object to come into your field of view, but nothing is outside your field of view there. So the horseshoe mount, which has become synonymous in a sense with the Hale telescope itself, the 200-inch telescope, that was why it came into existence, to get around the Hooker restriction of not being able to look in that direction. What about the mirror itself? This is a view looking into the side of the Hooker mirror. So there's the surface of the mirror at the top, coated in metal to make it reflective, and we're looking into the glass from the side, which is sort of a little less than half a metre or so thick. But you can see how the molten glass was poured into a mould, and part of it solidified, and then a little more was poured in, and a little more solidified, then a little more was poured in. So it solidified into these layers, and perhaps you also notice loads of air bubbles, which they couldn't get out. And air expands and contracts at different rate to the glass. So again, if you were to warm this up or cool it down, it would distort the mirror until everything had acquired an equilibrium temperature. So this was an absolute mess unless you could guarantee that your mirror was at the right temperature before you started the evening's observations, which is very difficult to get right. So the question is, could you scale up a 100-inch mirror and make it 200 inches? Surely that just means twice the diameter, 4 times the area, twice as thick. All you need is a mirror 8 times more massive, and surely that will still work. Well, it would in principle, but it would still suffer from how long will it take for this mirror to come into equilibrium. It would take probably more than all night before it got to the right temperature. Not only that, if you're pouring molten glass into a mold to make the mirror, then you have to think, how long am I going to cool that down to make sure I don't introduce any stresses? You're starting at well over 1,000 degrees and you want to bring it down to room temperature. You don't want to cool it too fast, otherwise you'll stress the glass, and that's the last thing you want if you want a nice uniform glass structure. So they calculated that if they built the 200-inch mirror out of plate glass, how long would it take to cool from being molten to being room temperature without stressing the glass? They calculated that process would take approximately 10 years. So they decided maybe that's not such a good idea. We need something radical. We can't simply scale up 100 inches to 200 inches. We'd have the same problems with distortions, and it would basically be way too heavy. So Hale had the idea, let's go with this newfangled stuff called low expansion glass. Most of us know it as Pyrex, borosilicate glass. You can take a dish out of the oven, stick it under the tap and cool it down from hundreds of degrees to room temperature, and it won't crack, simply because it doesn't expand and contract at the same rate that plate glass does. Try that with plate glass, it would simply shatter. With Pyrex, you can get away with that. It still does expand and contract, but at a much smaller rate. The actual number of microns that it gets bigger and smaller per degree is much less. So instead of taking 10 years to cool down from molten, you can probably get away with less than 1 year after making it. And that's a real advantage. But you still don't want it to be 10 times heavier. Remember, 4 times the area, potentially twice as thick, 8 times the mass. So they decided to come up with some innovative way of making a glass mirror. So he went to the Corning Glass Works on the other coast, on the east coast, and said, let's figure out how we can do this. How do you normally make a mirror? You have a mold, and you basically pour molten glass into the mold until it fills up, and then you have a pancake, effectively, which is flat on the bottom and roughly flat on the top. It doesn't matter if it's perfectly flat or not, because once you have a pancake, you then allow it to cool over many months or possibly years, depending on the size of the blank. Once you've cooled it down to room temperature, then you can start grinding that front surface down until it's the right shape. And when it's the right shape, you can cover it with a little film, a thin film of metal, and then you have the right shape for focusing your light from the distant galaxy or the distant star. So that's how conventional mirrors were made up to this point. But the radical idea they had was, let's do that slightly differently. What if we put a whole load of cores, fire bricks, inside the mould and then pour the glass into the mould? The glass flows around the fire bricks. Okay, you still have to then wait until that thing is cooled down from molten down to room temperature, but again, hopefully this only takes a few months. Once it's cooled down, you take the fire bricks away. And you're left with a surface. You still have to grind that surface down. You grind the surface down to the right shape, and then you cover it with a thin film of metal, and you've got your mirror, the front of which is identical to before, but the back of which now has loads of air gaps in it. And effectively, you've generated lots of ribs of glass. You've taken away a lot of the mass, but you've left all of the strength. So this is a very rigid mirror that is not going to flex much, and yet it's not anything like 8 times the mass. At most, it's something like 4 times the mass. So you've saved at least a factor of 2 by putting these fire bricks in the mould, pouring the glass in, and then removing the fire bricks. That's what the mould actually looks like. 5 meters across, 200 inches or 5 meters. And here are all the fire bricks of different shapes, and you'll see why they have this particular shape shortly. And the gaps between them, when you pour molten glass into this mould, the molten glass will flow in between and hopefully generate the ribs that we'll see shortly. There's a large plug in the middle there because this is going to be a Cassegrain telescope which requires a hole in the middle of the primary mirror. So I appreciate you can't see the detail. This is just an idea to give you a layout of the Corning glassworks. There's a big oven with the mould in it that we were just looking at, the mould with the fire bricks where we're going to pour the molten glass. Over on the right-hand side, we have a large tank full of 50 tons of molten glass. And then we have teams of people with large ice cream scoops. Okay, they're ladles, but they look like ice cream scoops, and they are going to periodically go to the tank, scoop out 100 kilos or so of molten glass, and then take it up to the mould and pour it into the mould. Backwards and forwards, hundreds of times, until they've shifted at least 20 to 25 tons into the mould. Let's see that in action. Here's the various workers putting the ladle into the molten glass. Everybody jumps on the other end to pull it out, and then you've got something like 100 kilos of glass. Water is sprayed onto the ladle to stop the ladle melting, because otherwise that would be a little bit of a problem. Remember, here we've got the ladle going into the bath, scoop up 100 kilograms of glass, scoop it up, bring it out, jump on the other end to balance it out, scrape away any excess glass, and you still need water sprayed onto the ladle. That's what that's doing there. And then the ladle is taken over to the oven with the mould. The ladle is taken into one of the windows and then tipped. You can't really see, but then tipped so the molten glass goes into the mould itself. Once that's done, the ladle comes out. Any excess glass is poured into a wheelbarrow, and the wheelbarrow is taken back to the tank and recycled. You don't want to waste any glass. This is quality stuff. So there's an indication, a still, if you like, of what's going on. 4 or 5 people on one end of the lever, the 100 kilograms or so in the ladle. You can see that most of the weight is actually taken by an overhead track system. So the people there are steering it into the right direction. And the guy at the front with this sort of face mask, he's holding this face mask with his teeth, by the way, to actually, given his hands are doing other things, he's then directing that into the mould and deciding where that's going to be tipped in to try and get a nice uniform glass in the mould. So there again is the team putting it in. The guy on the left must be a supervisor. I can tell that because he's wearing a hat. Not a hard hat, you notice. They seem to prefer fedoras in this particular age, but it gives you an idea of how the casting was done. This is 1934 when they first tried to get this mirror cast. It's the largest mirror by far that anybody had ever tried to cast. And they had a few problems. One of the problems was some of the fire bricks that are in the mould were not as secure as they had hoped, and they popped loose. And fire bricks are low density, so they float to the surface. Also, the oven itself is made of bricks, and it's, remember, heated and kept hot for a year, or thereabouts, depending on how long it's going to take to cool down to room temperature, some of the bricks on the inside became loose and fell into the mirror. So you ended up with an absolute mess on the surface of the mirror. By the time you'd cooled it down and gouged out the fire bricks and the bricks from the inside of the oven, you end up with a real mess of a surface. They seriously thought at the time, yeah, these gouges are really thick. I wonder if we can get away with grinding it down until those gouges are no longer there. But unfortunately, the gouges were just too many centimeters thick, and they couldn't do that. So they said, okay, we've learned from our mistakes. We'll do this again. In 1935, we'll have another crack at it. We'll make sure those fire bricks are absolutely bolted down, and we'll make sure the oven doesn't have any loose bricks in. And when they did it a second time, without the media watching them this time, previously they had reporters on hand watching what they were doing. This time they did it in private and they got it right. So the second casting of the mirror worked. And now you can see this is the back of the mirror, and you can see the ribbed structure that gives it its strength but not its mass. So here we have a couple of individuals who are basically shining light through the ribs to make sure the glass is as pure as it should be, no contamination, and they can also tell by looking at polarized light whether there's any stresses in the glass. And as long as there's no stresses in the glass, then it shouldn't distort the mirror when it warms up or cools down when it's in operation. That's simply a publicity shot from Corning Glass Museum, and it reminds you that the central Cassegrain hole in the middle of the mirror is about 1 meter in diameter, as you can see from the individual there. There's no particular reason to measure it, because if it's wrong, what are you going to do about it? So that's just to remind people that's how big it was. And again, it gives you a nice impression of the ribbed structure that you end up with due to the shape of the various fire bricks that were placed in position. The shapes are not arbitrary. They were decided such that you get the most likelihood of being able to support the mirror. For those of you who know about how you make mirrors, you have to make sure the mirror is supported correctly in its cell to make sure that if you point your mirror at the zenith or at the horizon, gravity isn't going to distort the shape of your mirror. It has to be supported very carefully to make sure that there is no perceptible distortion when gravity acts in different directions. So Corning were very happy at being able to make this, and they used it in their publicity. They said, we've just made a mirror, or they seem to call them eyes. It doesn't matter whether you're making lenses or whether you're making mirrors. When they're talking to the public, they seem to want to call these things the eyes. So they made an eye that sees that many miles. Why that many miles? Because it was calculated that when the 200-inch telescope was complete, it ought to be able to see 1 billion light years, and 1 billion light years is that many miles, 1 billion miles, 6 billion miles. They did have problems with the second mirror when they were cooling it down. They had earthquakes, they had floods, the ovens, the annealing ovens, which were keeping the mirror warm, gradually bringing it down to room temperature, they were being kept warm by electrical heaters, fed from a transformer. The transformers were on the floor below the oven, and when the river flooded, water came into the transformers. They had to decide, what are we going to do if the water hits the transformer? Are we going to interrupt the cooling of the mirror and have the mirror crack? Or are we going to wait until it goes bang when the water hits the transformer? It was a real headache, and they had to come up with some very interesting ways of getting around that problem, which involved, amongst other things, temporarily cutting the power, moving the transformer, and then reconnecting the power, and doing it before the mirror had a chance to realize it wasn't cooling down at the right rate. So amazingly, it all worked. And this is the mirror being taken from Corning back to the California coast. So this is a 20-ton mirror being supported on a strap, apparently, and then being manhandled by a group of individuals. Again, this is translucent, so light behind the mirror, you can see it shining through, and again, you see very clearly the ribbed structure of the back of the mirror. Once you've got it in the California optical shop, you can now say, right, we've got a 20-ton blank, let's start grinding it down to the right shape. A sphere to start with, and then eventually a parabola. That's going to take a while. 21 men 11 years to grind it down. Now, it took rather longer than planned for reasons I'll come to in just a few slides' time. But it ultimately took a team of 21 people something like 11 years before it was complete, to the point where they said the mirror is finished. That's what it actually looked like. It was actually ground on a turntable that was horizontal. And you can see some people applying the grinding solution in between a tool and the mirror blank itself. But how do you make sure you're grinding it to the right shape? Well, you have to test it, usually with a knife edge test or something like that. But to do that, because of the nature of the optical workshop they were in, they had to turn the mirror such that the mirror was vertical. Again, a reminder that it is absolutely critical. If you want to grind it in one position and test it in another position, you have to be absolutely sure the mirror is not distorting in between. So supporting the mirror was an absolutely critical part of the whole process, and is an engineering marvel in itself, but I don't have time to talk about all of those details. So they spun the mirror until it was vertical to do the testing. I thought this image was quite interesting because no, the guy in the front is not doing the hoovering. That's a little electromagnet. They're basically trying to make sure they picked up every tiny scrap of metal that might be in the building to make sure that nothing is going to scratch the surface of the mirror. But I also find it interesting if you look at the people in the top left and the top right, they appear to be smoking pipes. I don't think they were actually smoking tobacco. I don't think that was allowed in the optics room. But I presume that people just like to have an empty pipe in their mouth because that's what they're used to. And so even if they weren't actually actively smoking tobacco, they still had pipes. I thought that was quite intriguing. So you do a knife edge test to see if you've got the mirror close to the right shape. And the knife edge test involves somebody at one end of the lab and just basically saying how close are you to the correct figure, and then you keep grinding until you're as close as possible. So there's a blow up of the guy doing the knife edge test. And again, it was a very manpower intensive process. Grind a little bit, do a check. Grind, make sure you're doing it right, do another check. Backwards and forwards, backwards and forwards. At the same time the mirror was being made, they were making advances on the observatory itself. This is now 1936. Remember, this is a slab of granite, so all you have to do is basically drill a few holes into the granite and your mount and your observatory can bolt straight onto that. So it didn't take long before the steel work started to take shape. When it came to the point of, right, we now want to make a track on which the dome is going to rotate, the engineers said to Hale, well, you want this dome to rotate? Yeah. How accurately do you want the rails that we're going to make? Hale said, the nearest thousandth of an inch should do fine. Bear in mind that the dome that's rotating on these rails weighs about 1,000 tons. And yet Hale insisted that when the dome moves, the telescope would not be aware of the fact that the dome itself was moving. In other words, the dome motion would be so smooth it would not introduce any vibrations which would interfere with the operation of the telescope. So they tried to make these rails as smooth as possible, and then they could continue building the rest of the dome, all 1,000 tons of it. By 1937, it starts to look a little bit like a proper observatory dome. And here's one of the drawings of Russell Porter, of which I put a load on the back. I hope you've had a chance to have a look at them before coming here to your seat. These drawings by Russell Porter are absolutely amazing pencil and charcoal drawings made by a technical artist called Russell Porter, who imagined what it was going to look like. This was before the 200-inch was built. He knew what it was supposed to look like. He knew about the plans and the design. And in his head, he figured out, if I were to cut away the telescope, the mount, the observatory dome, what would I see? And then he produced these absolutely phenomenal drawings, which, as I say, I'll use a few of them, but most of them are on the table at the back there if you want a closer look. And I'll also make them available to you via Chris after the talk. So let's just take one of his drawings and let's just take some of that drawing away to remind ourselves how this telescope actually works. We have a 200-inch mirror down the bottom there, the primary mirror, and the prime focus comes up to the top, which is a cage in which the astronomer can sit. This is the first telescope that's large enough that the astronomer can be inside the telescope. And any telescope that comes after this, well, you could argue there's no need for the astronomer to be inside the telescope because now we've got photographic film and CCD cameras, so there's no need for the astronomer to go climbing into the telescope. But this was almost unique in the sense that it was a telescope big enough to do that before the technology changed. So there's an astronomer sitting at the prime focus of the mirror if you wanted to take images or take data at the prime focus. Alternatively, mirrors could fold into position below the astronomer's position there. So for instance, a secondary mirror could be used such that the light would hit the primary, the secondary, and then go through a hole, which I haven't shown, in the primary mirror. That's why we had a plug in the mold to make sure there's a hole in the main mirror about a meter or so in diameter, and that gives you Cassegrain focus. A longer focal length, which for some cases is what you want. Also, it means that you can put an awful lot of equipment at the Cassegrain focus. You can put hundreds of kilograms there without completely overloading the telescope. It's been estimated, though I don't think it's ever been tried, that you could put up to 1 ton of instrumentation behind the mirror if you wanted to have a spectroscope or something like that. Another possibility is to put a third mirror in position to make a dog leg or an elbow and hence give you a coude focus. Hits the prime, hits the secondary, hits the third mirror and sends it down the polar axis to a point there where you can see again astronomer standing. The point of this particular coude focus is partly it's a much longer focal length. It's a huge focal length which gives you a great magnification, but that point does not change in space regardless of where the telescope is pointing in declination or right ascension. So it doesn't matter where in the sky you want to point, the coude focus is always there. So you can put really heavy equipment, things that weigh many, many tons can be placed there without worrying about overloading the telescope. Let's have a look at how the telescope itself was constructed. There's Westinghouse, who attended to actually produce the metal work. There's a few of them inside the base ring which holds the mirror cell. Here's a few of the pieces being made, the horseshoe, some of the telescope truss itself. When most of the pieces were made, they were all bolted together to make sure they all fit together before they were dismantled and sent over to California. So here in the works, they have a sort of a topping out ceremony, if you like, before it was all dismantled. You probably can't see, but on the right-hand side, one of the dignitaries is Einstein. He's a theorist, but he was interested in knowing if a telescope like this ever gets built, you will be able to see galaxies so far, you'll be able to verify some of my theories of the theory of gravity or the general theory of relativity that came along in 1915. Rumour has it, though it's probably apocryphal, that Mrs. Einstein was there as well, and I think she asked, well, what's a telescope like this for? And somebody told Mrs. Einstein, well, you see, with a telescope like this, we can look out into the universe and we can pretty much tell what the structure of the entire universe is. To which Mrs. Einstein said, phew, so what? My husband can do that on the back of an envelope. So here's some of the bits being made. This is part of the horseshoe, a couple of people inside. The individual pieces of the inside and outside of the horseshoe are 4.5 inches thick, and they were made into the right curve with a forge press that could deliver 12,000 tons to make sure that you can take this sheet metal and bend it, even if it's 4.5 inches in thick. There again is another publicity shot of the horseshoe. Why you would bother measuring it? Because at this point it's too late to change it. So again, this is just to give you an idea of scale by having people poke through there. So again, this gives you an idea. There's the horseshoe made in 3 pieces and bolted together. The horseshoe weighed 170 tons. And given that this is a bearing surface, that lug on the right side would be removed. It was simply there to make it easier to move this thing around. The bearing surface is the outside of the horseshoe. That's what's taking the weight of the telescope. And so that outside curve had to be ground to the right shape, almost but not quite circular because of the weight of the whole mass of the telescope. That was then ground to approximately 1/1000 of an inch of the right shape. And then when they were happy that the horseshoe was made exactly right, it was dismantled and sent over to California. The south bearing looks a little bit like a sort of telephone handset. It's where the two arms of the yoke, which are supporting the telescope, when they come to the south end, there's the south bearing, and the two top and bottom are where the actual cylindrical yokes themselves are going to be mounted. There you can see the two cylinders of the yokes mounted to that sort of telephone handset at the south end there. It's a reminder that the actual yokes themselves, the actual cylinders, are empty. They have to be, because where else do you put the declination drive other than inside one of those? So yes, it has to be hollow, and it's easily large enough to take a man as well as a whole load of equipment. All of this, once it arrives in California, has to go up that grade in order to get it to the top of the mountain. So remember, a very, very windy road. Everything, no matter how heavy, has to go up that windy road. As far as I know, nothing fell off any of these lorries or trucks. In this particular case, I think it's part of the horseshoe going up. There's quite often a truck with the horseshoe, or the piece that's going up, another truck in front pulling, and another truck behind pushing. So basically 3 trucks are making sure this thing goes up the hill. You might not be able to read it, but the company involved is Hazard and Sons. As far as I know, it was all successful. Once each piece arrives, it goes into the observatory through a hatch in the observatory floor. I'm not quite sure why they didn't put it through the opening of the dome. Perhaps the dome opening was simply not large enough, and it was a lot easier to make a large square hatch in the observatory floor. So everything came through at ground level and then up through the observatory floor. There's the south yoke arriving. There's part of the horseshoe arriving with part of the tube truss already visible on the left-hand side. And then, like a big kit, they started putting it all back together. It all fitted together when it was on the east coast. Hopefully it still all fits together when they start putting it back together in the west coast. So there again, the tube is starting to take shape. Notice that we have a worker standing on the telescope. No need for health and safety, no need for harnesses, no need for hard hats. They're for wusses, basically. So these are real men, remember, in the 1930s. This is 1939 now. And again, okay, this case, the guy has got a hat, but again, it's a fedora, not a hard hat. So here he's working on the prime focus cage. This is where the astronomer would sit in order to take prime focus photography or prime focus images. So here they're climbing over the superstructure, and here they're testing whether or not the telescope can see all the way south. They know it can fit into the horseshoe in the north. How far south can it go? It'll never actually point at the south horizon because there's San Diego there. But how far can you go down? Here, a couple of engineers are just checking it out. I think they're engineers because they've got the sleeves rolled up, so they probably are. And they're basically just making sure how far down this can go. Of course, you need some rather serious gearing to make sure that you can drive the telescope in right ascension and declination. So as well as the problem of making the world's largest mirror by a factor of something like 4, and you've got the largest superstructure to deal with, you also have the problem of, well, how are you going to drive it? By the time you've got a mirror inside a steel truss, inside a yoke which is supported by a horseshoe, you've got about 500 tons of telescope. And you want to be able to move that across the sky. Again, the engineers would ask Hale, well, how accurately do you want to be able to move it to any particular point in sky? Hale said, well, I'm not that fussed. An arc second will do. So they ended up building machinery that could move a 510-ton telescope with a precision of order arc seconds. It was like, at the time they said, it's like building a battleship, but with the precision of a Swiss watch. So how do you drive something that big? Well, you have a right ascension and declination gear that look a little bit like this. They weigh tens of tons in their own right. And you can get the scale either from the man standing in the middle or the fact that there's a little hatted man popping up from one of those little windows there. So you need to be able to make sure that this is A, absolutely rigid so you can drive the telescope, but of course you've got to make sure that you make all of the teeth of your right ascension drive and your declination drive absolutely precise. There's no way you can point the telescope with arc-second precision if you want to be able to use it as a go-to telescope, unless you've got the teeth very, very accurate and precise. So that took them years as well. In parallel with making the mirror, in parallel with making the observatory, they had to cut the teeth of the right ascension and declination gears. And that took a lot of time, a lot of effort. So they had a system by which they could slowly grind the teeth to the right shape. And when they grind the teeth to the right shape, they then polished them until they were essentially the perfect shape for the worm. So here they're being polished. How do you know when you've got the teeth absolutely right? Well, the quality control involves basically getting a man with a pipe to run his finger over each tooth, because the amount of errors you can feel is actually better than they could actually determine with the technology they had. If the person with the pipe said that, yep, all of this is absolutely smooth, I can't feel any roughness here, they knew they were getting close to where they needed to be. And then finally, you have the worm that actually drives the worm wheel to give you the right ascension and the declination drives. If you want to be able to move 500 tons and slew it as well as simply tracking is relatively straightforward, but you need to be able to slew it as well. And then you ideally want to be able to move to different parts of the sky in hopefully no more than a minute or so to different chunks of the sky. So how big a motor do you need to make sure you can move a telescope like that? It's an absolutely enormous motor that you can see here, and when we look at the scale, we can see it's actually about that big. The telescope itself was made with sufficient precision, and the horseshoe mounting was made such that the friction was so low. It was something like 1,000 times less than the friction you would get from a bull race or something like that. It was made by floating on oil. So the friction was so low and the balance was so good, you needed a tiny fraction of a horsepower motor to actually move it around the sky. So I'm not going to dwell too much on Russell Porter's drawings that were made sort of between 1937 and 1940, but I do invite you to take a closer look at some of those in the back. And I will also make them available to you as PDFs so that you can put them on your computer screen and really blow them up to see the exquisite amount of precision that he's put into showing, for instance, how the drives were actually done. There's loads of cams and gears and motors down here driving two huge right ascension drives. Not only were they precise in what they did, they also had plans for building analog computers out of cams and gears that would take into account, if you wanted to point it at a particular point of sky, it would take into account the refraction of the Earth's atmosphere, which would move a star by a few arc seconds away from where you would expect it to be. That would be built into the drive mechanism. They had really fantastic ideas. Again, inside the yoke arms, there's one of the cylinders of the yoke. Inside, there's a man for scale. There's the declination drive, because that's where the declination motors are, inside the cylindrical yokes. That's what it would look like having an astronomer in the observing prime focus position there, and that's a close-up of a random astronomer sitting at the so-called pedestal. That's the prime focus point. Where you would either have an eyepiece or more likely a photographic plate to take images. Whether or not all astronomers wore a suit and tie, I don't know. I don't think that's probably very likely. And whilst taking an image, if it was over many, many hours, which of course with photographic plates it might have to be, then the astronomer had the option of making tiny little corrections in north, south, east, west to make sure everything was perfectly aligned on the distant star, galaxy, whatever. And it looked like everything was going really hunky-dory. It looked like it was just months away from being finished. The mirror was ground to within a few millionths of an inch to what they thought was going to be the right shape. So they thought, right, we're almost there. And all of the steel work in the observatory was basically done. So they thought, we're only a few weeks away from being finished, maybe a few months away from being finished. But It's 1941. And the USA was dragged into the Second World War. Well, better late than never, I suppose. So the various machine shops and optical shops were then repurposed for the military, and everything was mothballed and didn't come out of mothballs until, as you know, 1945. So now we hear in 1945, the mirror comes back into the optical shop. Perhaps you can just about see there's a little bit of a dish. You can now see that the mirror isn't just flat on the top, it has a dish shape. Also notice that we now have some women on the team. Great. It started with 21 men, but eventually there were women on the team as well. And so the grinding continued for a little while until they were absolutely sure they'd got it as good as they could get it in the laboratory. But of course, the real test for any mirror is not testing with a knife edge in the lab, it's actually get it on a star and see if the star images are perfect. So they basically put the mirror in a box, took it up the incline and got it to the observatory. And in 1948, 77 years ago, the 200-inch telescope was then named. Unfortunately, George Ellery Hale had died a little time before and never actually saw it completed. But at this point, the 200-inch telescope was named the Hale telescope. And that's why I regard this as being the 200-inch is 77 years old, because it's 77 years since the dedication ceremony. They still had a tiny little bit of work to do. The mirror was not yet silvered. It didn't have any aluminium or silver coating, no metal coatings, just glass. But they wanted to be sure it was focusing stars correctly. So they put the mirror in the telescope, focused on a star, and tried to work out if the star was perfect. If the star wasn't perfect, which bit of the surface of the mirror is a little bit too high and needs to be ground down a little bit more. So these tiny little white dots you can see are not dust specks on the image. Those are little bits of tape in which they've identified this bit is a few millionths of an inch too high. This bit is a few millionths of an inch too high. And the master polisher there would then have the job of trying to get that down to a perfect finish. And he would do his best. The telescope would go back into, the mirror would go back into the telescope, focus on a star, try and work out whether the star image was perfect. If not, bring it out, do a little bit more. The final corrections were probably no more polishing than a tiny bit of jeweler's rouge on his thumb and just gently wipe the surface. That would be enough to take a millionth or 2 millionths of an inch off, and that was the final correction. By 1949, it was declared, we are done, and then we can take first light. There's, again, a publicity shot of an astronomer. We've gone from a suit to a lumberjack's outfit by the looks of it. And again, a reminder in the drawings, that's the astronomer in the prime focus cage. Edwin Hubble, who had done a lot of work on the Hooker telescope, looking at galaxies and measuring their recession velocities. And we were coming to the conclusion, of course, in those days about the expansion of the universe. It was rather important that he did some work on the Hale, because, of course, that meant that he could look further at more distant galaxies and verify the Hubble law that the more distant galaxies are receding from us even faster. I'm sure, because it was quite cold, they were quite pleased with the idea of having war surplus flying suits that are electrically heated, because remember how cold it gets up there in winter. So yes, they're open to the elements, so they stay toasty warm by wearing these flying suits. So this is apparently a lumberjack who's doing some work there, and he's showing you how it would work. You put a photographic plate holder into the prime focus position. Again, we're in the middle of the prime focus cage here. The plate holder would be locked in position, and then the film would be placed. No, whoa. No, the film is there. So, yeah, in the dark, the film would be taken out and then placed into position. And then the back of the camera, that's it. Then the back goes into position, and then that locks into place. And now you are ready to double check everything is right. So you want to make sure that you are looking at the object you think you're looking at. So there's a little eyepiece on the side there. You can find a guide star, put it in the middle of crosshairs, move it if necessary until you've got a guide star, and that you will use to make sure that the telescope is tracking accurately. So you will set up the guide star in your little side eyepiece. You will then do a double check. Have I got my sandwiches for the night? Yeah, okay, the sandwiches are all set. So I'm ready to go. So I can expose the plate, and now I can basically say, right, we're now in business. And every once in a while, you check the eyepiece, make sure the star is tracking accurately, and if necessary, move the telescope slightly up, down, left, right. And that brings us to 1951. Basically, the scope is now operational. It was first light as of 1949. And 2 years later, they took this picture of the Horsehead Nebula. And some years after that, I saw it in a book in the school library. And that changed my view of the universe. A reminder that it's still doing good work, because although it's no longer the largest telescope in the world, it is still a very useful test bed. It's still a 5-meter mirror. It's not by any means the biggest in the world, but it's only about half the size of the biggest in the world. And if you put different instruments on the back end of the Hale telescope, you can test out technology. So for instance, on an image of Ganymede back in 2013, they tested whether or not adaptive optics could improve images from ground-based telescopes. And one of these telescopes is taken with the Hubble Space Telescope, and one is taken of the surface of Ganymede with the Hale telescope with adaptive optics. And it's not the way around you think it is. No, it's the Hale telescope with adaptive optics on the left, and it's the Hubble Space Telescope image on the right. In other words, with the large mirror on Earth, if you get the technology right, you can actually do better than the Hubble Space Telescope. And once you proved it on the Hale, you can then say, yep, this technology, I'll tweak it until I've got it right. Now that technology has proved itself, I can use it on other telescopes around the world. So it is still a useful workhorse, even though it's not the largest telescope in the world anymore. Because it's in California, it still needs its mirror to be cleaned every once in a while. So every 18 months or so, they lift the mirror out from the bottom of the telescope, and then they clean it. If you're of a nervous disposition, look away now, because it's not quite as vicious as it looks. They clean the surface, and then they apply a little bit of weak acid to take away the metal surface until they reveal the transparent glass underneath. And again, you can now see the ribs of the underside of the mirror, even though we're looking at a polished top side. So they give it a damn good clean until they are absolutely sure it is effectively back to its pristine state without changing its shape. And then they would put it into an oven and evaporate another film of aluminium to hopefully use it profitably for the next 18 months or so. So the Hale telescope was the largest telescope in the world when I was born. It was the largest telescope in the world for all of my childhood. It was the largest telescope in the world for most of my adult life, and was only overtaken many decades later. It was essentially the best telescope in the world for half a century or so. And there aren't many scientific instruments that can make that sort of claim. And the fact that the telescope has been so useful for so many decades is testament to the scientists who designed it, the technicians who built it, and above all, the man who had the vision to bring it all together, George Ellery Hale. There's my acknowledgements, various information from Caltech, Corning Glass Museum. I think those web pages have actually moved. And I've taken a fair bit of information from a book called The Glass Giant of Palomar, and I've taken the Russell Porter images, which are reproduced on the back table there, from various publications that have been published, and some of which are available from Caltech. So I believe the Hale telescope is an amazing piece of engineering and an amazing piece of science, not only because of my love affair with it, because it was the world's largest telescope when I was influenced to think isn't the universe an amazing place? Thank you all very much.